Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this playlist, we've been looking at group theory, which is a way of studying symmetry. And what's really interesting about group theory is that you can actually use symmetry to study groups. Okay, so in other words, you use group theory to study group theory. And it's one of those fields of mathematics where you can do that. And what I want to show in this video is a very, very simple example of this, and a very important example where we come up with Lagrange's theorem. And the thing that's going to allow us to do that is the notion of cosets, which is absolutely fundamental to group theory. Okay, so let's introduce what cosets are. So remember, if we want to have a notion of symmetry, we need to talk about permutation representations, okay, or equivalently, group actions. So the setup I want to have a look at here is I have a group G, and I want to look at subgroup H of G. And the group action I want to have a look at will be the right regular action of this subgroup H on G. So we're going to have an H set, and the set itself will be G. Okay, so let's remind ourselves what that right regular representation is. Okay, so what's H dot G? If little h is in big H, and little g is in big G. Okay, H dot G was defined to be GH inverse. Okay, so here we have an H action, and hence this is a notion of symmetry. Once we have an H action, we can talk about H orbits. So let's look at the H orbit of some element in this set, so some little g. So H dot G, what is that? So remember, as is suggested by this notation, it's just the set of all elements of the form little h dot G, where little h runs over all of this big H. So it's all these elements, these GH inverses. In this case, H belongs to this group. Okay, so these inverses, as H runs through all the elements of this subgroup, H inverse also runs through all the elements of this subgroup. Okay, so certainly H inverse is inside big H, and every element of this H is an inverse of something. So this is actually the same as the set of all GHs that you can get, where this little h runs through all of H. And that's because essentially this H is closed under inverses, and so inverting elements here gives you a bijection from this set back to itself. Okay, so this is just the same as this, except for the way you've listed the elements is just jumbled up. It's a permutation of the list of elements here. Okay, so this is a very, very important H orbit. It's called a coset of H, and it's the coset of H containing G. And because it's the set of all these elements, we will write it in this notation, which is the standard notation for a coset. Okay, so it's little g and a big H. So in other words, the set of all little g times little h's here. And that's our notion of a coset. Okay, so before moving on, let's just look at a simple example so that we can understand what this is. So suppose we have the dihedral group of order 4 times 2, 8. Okay, so it's the symmetries of the regular foregone, so it's just the symmetries of this square. So I've put the square here with side length 2 and center at 0. Okay, so that's our starting group, and we're going to look at this subgroup H. Okay, and what subgroup is that? It's going to be given by the following 2 elements. Okay, so remember, this group has 4 rotations and 4 reflections. Okay, so let's consider the 4 reflections. You have the reflection tau 0 about, say, the x-axis, a reflection here tau 1 across this diagonal, reflection tau 2 across the y-axis, and a reflection tau 3 across this diagonal here. So we're going to look at the group that consists of just 1 and tau 0. So 1 and this tau 0. And it's quite easy to check that this actually forms a subgroup. Okay, it's closed under 1, so it has a 1 here. It's closed under products because tau 0 squared is equal to, well, it's a reflection, so when you do reflect twice, you'll get the identity, so that's just that. And of course, any other product has to be inside here. And it's closed under inverses because this is its own inverse, and a reflection is also its own inverse. Okay, so that's a subgroup, and we can ask for the cosets of this. Okay, so remember, these are H orbits inside here. So in particular, they'll give a decomposition or a partition of this group here. Okay, so the first one that's always important to note is that you can look at the coset containing the element 1, 1H. So that's 1 times all the elements in the subgroup H. Of course, when you multiply by 1, it doesn't do anything, so it's just equal to this H. It's just this set here. And remember, this is just an H orbit, so this is an equivalence class. So of course, you can write this as the equivalence class of anything inside here. It's also the H orbit of tau 0, so this is also tau 0 H. So this coset of H containing tau 0 is the same thing, it's also H. And you might want to check that if you multiply these elements by tau 0, you get tau 0 here, and tau 0 squared, which is 1 here, so you just swap them around, okay? So this is one coset that you have, although you've written it in two different ways, 1H and tau 0H. Okay, let's look at another more interesting coset. So we're going to look at the coset containing tau 1, tau 1H. So according to this, you just look at all the tau 1 times elements in this subgroup. So you get tau 1 times 1, which is tau 1, and you get tau 1 times tau 0. That's the other element. So this is a product of two reflections, this reflection here and this reflection here. So it's a certain rotation, and it's quite easy to work out which rotational symmetry of the square that actually is, okay? And to work it out, I guess the easiest way is you can just look and see what happens to the positive x-axis. Where does that get rotated to, okay? So remember, this is just composition of functions. You reflect about the x-axis first with tau 0. So the positive x-axis, when you reflect, stays put. And then you're going to reflect about this diagonal axis. So this positive x-axis gets reflected to the positive y-axis. So at the end of the day, you've rotated that positive x-axis 90 degrees in this anti-clockwise direction. Okay, so it's that rotation. So this coset has one reflection and one rotation. And again, remember, this is an H orbit of tau 1, and it's also the H orbit of everything inside here. It's an equivalence class. So if you look at the coset containing tau 1, tau 0, that's also the same coset. It's quite easy to see that these two have empty intersection, and that's what you expect because, remember, H orbits decompose this partition, this G. Okay, so I hope you can see what the other cosets are. Okay, so you've got H is one, tau 1H is another. Okay, if you do tau 2H, a similar calculation will tell you that you'll get the reflection tau 2 and another rotation. Okay, and so to get the last one, you need to use the last reflection, which is tau 3, tau 3H. So you get reflection tau 3 and another rotation. So there are two elements in each of these cosets, and there are 4 cosets here, so in total you get 8 elements. So that's how you've decomposed the 8 elements of this group into 4 cosets. Okay, so one thing that's rather nice is, well, do these have any meaning, okay, these cosets? And one thing to keep in mind, and will be important later, is suppose we want to look at this tau 1H, okay, this coset here. Which elements are these? Okay, do they have some sort of geometric significance? Okay, since we're studying the symmetry of the square, it should somehow appear there. So I claim that the elements in this coset are precisely all the symmetries which map the positive x-axis to the positive y-axis, the positive x-axis to the positive y-axis. Okay, so let's check the reflection tau 1 here. That sends the positive x-axis to the positive y-axis. Okay, so that works. And what about the rotation? Well, we just saw that this rotation, of course, is the one which sends the positive x-axis to the positive y-axis. Okay, and it's quite easy to see that any other rotation will send the positive x-axis somewhere else, and similarly, any other reflection will send the positive x-axis to somewhere else. Okay, so this is something that you can do with each of them. They're determined essentially by where you send the positive x-axis. Okay, so let's look more generally at what's going on. So something that we saw here is that each of these cosets have the same number of elements, 2. And that's part of general phenomena, okay? And that's what's written in this next proposition here, okay? So if you're given any group element inside big G, in fact, not just inside H, inside G, then the cardinality of that coset is the same as the cardinality of H. Okay, so in other words, all these cosets have the same cardinality. Okay, and proof of this is actually quite simple and instructive to have a look at. Okay, so to do that, I just need to construct a bijection between the two sets, these two cosets. And how do I do that? So I want a function from h to gh, and there's a very natural one. So what are the elements of gh? They're things of this form, so I can map h to gh, right? And that's a function. That's a well-defined function, and it's quite easy to see actually that it's surjective by definition of what this coset is. But to see it's a bijection, actually the easiest way is to construct the inverse bijection. So now I want to invert this map by going from gh to h. And of course, what you want to do is you want to send gh to h, and the question is, well, is that legitimate? Okay, how do you map gh to h? Well, I guess you want to just remove the g, but how can you be sure that you can actually do that? Okay, and the point is that in this case, removing the g, what does it correspond to? How can I remove the g? Well, we're in a group. Okay, so you have group inverses. So I can multiply this element by g inverse on the left. Okay, so that's a well-defined thing, okay, to multiply on the left by g inverse. And of course, the group axioms say that g inverse g is 1, and 1 times h is just h. So indeed, this is a well-defined map which inverts this map here. That gives the bijection between these two cosets, so all cosets have the same cardinality. The notion of symmetry is really tied up mathematically in the notion of a g-set or group action. So a very, very natural question is, can you construct lots and lots of examples of g-sets that you understand well? And it turns out that you can construct, so to speak, a stereotypical example, and what it is based on is on the g-set G mod h. So here h is a subgroup of G, and we're going to manufacture a g-set G mod h. So this is already a set, it's a set of cosets, and I want to put a g action on that. And that g action is encoded in this next proposition here. Okay, so the proposition says that g does act on this G mod h. How? Well, how does a little element g inside big G act on an element on here, which is just some coset fh? Well, g dot fh is just gfh. Okay, so the way you read this, of course, you can read this in two ways. One way is that it's the coset containing of h containing gf, and another way to read this is just by looking at it, as suggested by the notation, it's the set of all gf little h's where the little h ranges over all of big H. Okay, so note that in a group we have associativity of multiplication, so there are two ways to look at this. You can bracket the first two together, in which case you have gf times all the possible little h's, so that's precisely this coset here. But another way to look at this is it's g times all the fh's, and where the h ranges over all of this. So all the fh's is of course just all the elements in this coset, so it's g times all the elements in this coset. That's the other way to read what this is here, okay? And that comes from associativity of group multiplication. So it's quite easy to prove that this is actually a G action. You just need to check the axioms for a G action, and it's exactly the same as the check for the left regular representation of G on G. Something else that's special about this particular G action is that it contains a single G orbit. And it's quite easy to see that too, okay? So to be a single G orbit, let's see what happens when you put f equals 1 here, okay? If you put f equals 1, let's see what the G orbit of that coset 1h, which is just h, okay? So what you get is f equals 1, so you'll get all the GHs. And all the GHs means you get all the cosets, which means all the elements inside this orbit space. So this is just a single G orbit. Okay, so that's rather nice that we have this fact, okay? So given any subgroup of a group G, okay, we immediately get some sort of a G set, G mod H. Let's look back at our example that we looked at before, example 1, where the group was the symmetries of this square. We have the 4 reflections here, and we looked at the subgroup generated by this reflection tau 0, so it just consists of 1 and tau 0, and we saw that there are 4 cosets, okay? They're given by the cosets of each of the reflections. So there's the identity, so I guess there are 4 reflections, and the reflection containing tau 0 h is also h, and then you have the other 3 cosets, tau 1h, tau 2h, and tau 3h. Okay, so you have these cosets. And what I claim is that G acts on this set of 4 elements, on this set of cosets. Okay, and let's see how that works. Okay, so rather than giving you a full description of this G action, let's just see how the elements of the group permute these elements here. So remember, there's a permutation representation. G maps to the permutation group on this set of 4 things. Okay, so each element of the group will permute these 4 things. So for example, you might want to know, how does the element tau 1, this reflection here, permute these 4 cosets? Okay, so let's just see how that works, and it's quite interesting. Okay, so remember, how does tau 1 act? Well, it's just left multiplication. Okay, so for this H here, tau 1 will send this where? You just multiply this on the left by tau 1, so it gets sent to tau 1H. So that's what tau 1 does to that. Okay. Okay, so what about tau 1H? Where does tau 1 send that? Well, you just multiply on the left by tau 1. Tau 1 is a reflection, so its square is the identity. So that sends you back to H. So tau 1 just swaps these two. Okay, let's see what tau 1 does to this tau 2H, and that's more interesting. Okay, so it's worthwhile going through this. So tau 1 sends this coset to which coset? Okay, so let's look at tau 1 times tau 2. Okay, so this is an element that's in the image of this under tau 1. Okay, so let's see what tau 1 tau 2 is. So of course it's a rotation, being the composition of 2 reflections, and let's see which rotation rather it is. Okay, so let's look at the positive x-axis and see where this composite of reflection sends it. Okay, so first you do the tau 2, so tau 2 will send it to the negative x-axis, and then you apply the tau 1, which is reflection about here, so it gets sent to the negative y-axis. So at the end of the day, the positive x-axis has gone to the negative y-axis, so that's a rotation 90 degrees in this clockwise direction, a rotation 90 degrees in the clockwise direction. Okay, so this is a rotation, and this rotation has to be in one of these 2 cosets. Okay, so remember, each of these cosets contains 1 rotation. So which of these 2 will tell you where tau 1 sends this coset? Okay, so let's see what this is. We have to write it as an element of a coset, and I claim it's actually in the coset tau 3H. And that's because this is the same as tau 3 tau 0. Okay, so let's check that tau 3 tau 0 equals this. Okay, so what is tau 3 tau 0? Let's see what happens to the positive x-axis here. Okay, if you apply the tau 0 first, it doesn't do anything. And then if you reflect about this line here, the tau 3, it goes to the negative y-axis. So in fact, tau 1 tau 2 equals tau 3 tau 0. So of course, what multiplication by tau 1 does is it sends tau 2 to the rotation here, and it will send the rotation here to the reflection tau 3 here. So tau 1 will send tau 2H to tau 3H, and of course it has to send tau 3H back to tau 2H. So that's tau 1. Okay, and that's how it permutes the cosets. Okay, so let's have a look at another group element. So of course you can use any of the rotations or reflections. Let's look at tau 2, and I hope you can see what happens here. Okay, it's something similar. Tau 2 of course should swap H and tau 2H. Okay, and the same idea will show that tau 2 swaps these 2 as well. Okay, and you can do this for all the rotations inside G, as well as the 2 other reflections, to see how it jumbles up these 4 cosets. And it's already clear from this example here that this contains a single orbit. Okay, H. Okay, let's just apply some group elements to it. You can send it using tau 1 over here, tau 2 to here, and then tau 1 to here, and you've mapped it across all the elements here. So there's just a single G orbit here. And that's how this G set works in this case here. So that's great. We found a way of manufacturing a G set just from a subgroup of G. However, the only types of G sets that you can construct are those which contain a single G orbit. So you think, well, can you construct other ones? And the answer is it's very easy to construct others once you have that by the following technique. Okay, so we're going to look at R G sets, x1 up to xr. And what you can do is you can construct a new G set which essentially contains all of these, okay? So we're going to look at the disjoint union of x1 up to xr, okay? So basically, what we're going to do is we're going to pretend they're disjoint, so if need be, we replace each of these with a copy, which is disjoint from all the others, okay? So x1, you think if it's not got some elements in common with the others, you replace all those elements with things which are different from all the others, and you do that for each of the sets here, okay? So that gives you a disjoint union x, which we write like this. And the point is that now the G action on each of these extends to a G action on the whole of this set, on this disjoint union. And in fact, there's a natural G action which uniquely extends the G action on each of these, okay? And it's quite easy to see how that works. If you have an element in here, okay, that means it has to be in one of these. Let's say x is inside big Xi, okay? And you want to know what's the G action on that. So little g inside the group acting on this x. How do you define that? It has to be something inside here. Well, all you do is you realize, well, this little x, it's inside this xi, okay? It's only in one of them because it's a disjoint union here. And you let G act inside here. This is a G set, so G acts on this, and this will be some element inside this big Xi, and hence an element of this disjoint union. And of course, the fact that each of these gives you a group action, okay, G acts on each of these, allows you to check the group action axioms on this disjoint union as well. So in particular, if you replace each of these xi's with things of this form, so they're single orbits, you'll find that this is now a union of different orbits. In fact, here will be a union of R orbits. And in that way, we can construct lots and lots of examples of G sets, and they're ones which are really determined precisely just by the group and the structure of this subgroup. Okay, so if you know those two things, you know about this G set. Finally, I can state the beautiful Lagrange's theorem, which is an application of symmetry to studying groups, and in particular, the symmetry that I introduced by constructing the G set G mod H. Okay, so here we have this group G, which is finite. The number of elements in it, the cardinality of this G, is called the order of G. So it's a finite group of order, this cardinality of G. And suppose we have a subgroup, okay? So in this case, we have a relationship between the cardinality of G, or the order of G, and the order of H, okay? The order of G, of course, is bigger than the order of H, but actually it's a multiple of the order of H. It's the order of H times the number of cosets of H in G. So in particular, the order of H divides the order of G. So this is a beautiful, completely group theoretical result, okay? You have a group, a subgroup, and then you're saying something about the number of elements in each of those. There's some sort of relationship. And the way we'll prove it is using symmetry, okay? So the H action, in fact, that we looked at before. Okay, so remember we have this H action, which means that we have a partition of G into these cosets, so G1H up to GRH. And the number of cosets is R here, so that's a set of cosets, and the number is R here. Okay, so to count out how many elements are inside G, we just need to sum up the elements in each of these. So we have the sum from I equals 1 up to R of the cardinalities of each of these cosets, G, I, H. But remember, in that first proposition, each of these cosets have the same number of elements, the same as the number of elements in the group H itself, okay, which is the coset 1H. So there are R of these summons, so this is just R times the order of H. And that's precisely this result here, okay? So the order of G is just the order of H times R, which is the number of elements of cosets of H in G. Okay, so this is Lagrange's theorem and has many, many applications in mathematics. Okay, and I want to give you a really, really interesting example of that right here in this corollary. Okay, so suppose you have a group G which has prime order, okay, and the prime order is P. Then I claim that in fact you know what that group is. Okay, so remember, as a set it's got P elements, but to get a group you also need to put a multiplication on it. And I'm saying that essentially there's only one way to put a multiplication, in the sense that I can tell you what that group is up to isomorphism. Okay, so we already know one group that has P elements, and that's the group of integers modulo P, okay, the cyclic group of order P, Z mod P. This is the symbol for isomorphism, and I claim that any group which is a prime order has to be isomorph to Z mod P. Okay, so let's see how that works, and it's quite easy to prove this once you have Lagrange's theorem. Okay, so what we're going to do is we're going to start with some element which is not equal to 1 inside the group, say sigma. And remember, we always have this group homomorphism once we've picked such a sigma, an element of the group, okay? It goes from the group Z to G. What it does is it takes an integer I, and it sends it to the ith power of this sigma. So it's a group homomorphism, so we can look at its kernel and image. We're interested here in its image. And the standard notation for the image is this angle bracket sigma angle. Okay, so the image is just all the powers of sigma, both positive, negative, and also the 0th power, which is the identity. So all the powers of sigma, and we use this notation here, and it's also called the subgroup of G generated by sigma. And being the image of a group homomorphism, it's a subgroup of G. Okay, so we've got a subgroup of G, and once we have a subgroup of G, we can apply Lagrange's theorem. And that's where we use the fact that this is prime, okay? So since it's a prime order, so there are only the possible orders of subgroups, there's only two possibilities, okay? So it either has order 1, a subgroup, or order P. Okay, so let's see what happens here. Let's look at this image of this phi, this subgroup generated by sigma. It contains both 1 and sigma isn't equal to 1. So it has at least 2 elements. So the order of this subgroup can't be 1, because there are at least 2 in there, okay? So it's not 1, so it has to be the other divisor of P, which means it's P, okay? So the order of this is P, so that means that it has all P elements in this group. So that tells you straight away that the subgroup generated by sigma, the set of all these powers of these sigmas, is equal to the whole group. Okay, so that's a way to get at the whole group. This group just consists of all powers of sigma. That's all it is. And I claim that's enough to actually show that it is isomorph to Z mod P. Okay, so let's have a little think about this. Okay, so let's look at all the elements inside this group. Okay, it's all the powers of sigma. So we start with the 0th power 1 here. And we've also got sigma to the 1, which is just sigma, which doesn't equal 1. And let's suppose we just keep looking at higher and higher powers of sigma. Eventually, because this is a finite group, okay, and in fact there are only P elements, you have to eventually repeat one of the elements which is in here. Okay, so let's go to sigma squared. Okay, sigma squared, is it the same as either of these? Well, it is not the same as sigma. If sigma squared equals sigma, I guess you can cancel sigma from both sides, which will tell you that sigma equals 1. Okay, so this does not equal sigma. And let's suppose we're in the case where it doesn't equal 1 either. Okay, and let's suppose that we have, so let's suppose our prime is big, okay, and we can adjust this proof for small primes later, okay? So let's look at sigma cubed. Let's see, is this the same as one of the previous ones? Can it be the same as sigma squared? Well, no. If it was the same as sigma squared, you can cancel the sigma squared, then sigma equals 1, which we assumed wasn't true. Is it the same as sigma? If it was the same as sigma, then you can cancel the sigma, and sigma squared equals 1. We assumed that wasn't true. So it could be that sigma cubed equals 1, but if not, well then let's suppose it's not, just for the purposes of this picture, and we can keep going. And the basic point of this argument is that the first time some power of sigma repeats itself has to be, so maybe it goes all the way up to sigma to the k minus 1, and the first time it repeats itself has to be when it equals this one here. So let's suppose that sigma to the k equals 1, but this doesn't equal 1, and it doesn't equal any of the previous ones as well as a result. Okay? So what you'll have is that you'll have distinct elements, sigma to the 0, which is 1, sigma, sigma squared, all the way up to sigma to the k minus 1. Okay, they're distinct elements of this group G here. Okay, so what is this subgroup generated by sigma? It's all powers of sigma. So let's look at all powers of sigma. So you've got the first 0 up to the k minus 1 power of sigma. If you go to the kth power, you're here. If you go to the k plus first power, you're here, and so forth. So higher powers of sigma just stay inside here. What about negative powers of sigma? Well, this is sigma k equals 1. So sigma inverse is the same as sigma to the k minus 1. When you multiply this by sigma, you get sigma to the k, which is 1. And using negative powers of sigma, you get all of these. So this is in fact a complete list of all the powers of sigma, both positive and negative, and the 0th. And so it is the whole subgroup generated by sigma. But of course that subgroup is all of G. So it means that this must be a list of all the P elements inside this group G. So K equals P, and the elements of the group are 1, sigma, all the way up to sigma to the P minus 1. And we also have that sigma to the P equals 1. Okay, so now we know a lot more about this group, and we've got another picture of what this group looks like. Okay, these are all the elements listed out. Okay, and it's easy to know how to multiply them, and you know that sigma to the P equals 1. Okay, so now let's actually construct our isomorphism between our cyclic group of order P, Z mod P, and this G. Okay, and I hope you can see it's going to be induced by this one here. The residue class of I modulo P, okay, is going to get sent to sigma to the I. Okay, so it's easy to see that this will be a bijection. Okay, and the main thing here actually is to check that it's well defined. To check that it's a homomorphism is essentially the same as checking this is a homomorphism, and that's an easy exercise. Okay, so to check this is well defined, well, remember this is only a residue class, so you can change the I by some multiple of P. You can replace this I by I plus some AP, where A is an integer. And the thing is, to check this is well defined, you need to show that the corresponding power of sigma is the same. So sigma to the I plus AP has to be the same as sigma to the I, because these two elements have the same residue class modulo P. So what is this equal to? Well, it's sigma to the I times the 8th power of sigma to the P. And we know sigma to the P is 1, so this is 1 to the A, which is just 1. And 1 times this sigma is sigma to I. So this is actually a well-defined map which gives an isomorphism between Z mod P and G. Okay, so that finally proves this rather beautiful result here. Okay, if you have a finite group and you just happen to know that the number of elements in it is a prime number, okay, it has P elements where P is some prime, then as a group you know precisely which group it is. There's only one possibility. It's isomorphic to the cyclic group of order P. And the way we prove that is based on Lagrange's theorem, which simply uses symmetry to study the group. Okay, so in this case, the H action on G to partition this G into cosets. I hope you enjoyed this adventure in pure mathematics.